So we are having lecture 21, EE341, microelectronics. Just for more better synchronization and a little bit more proper drawing, I'm just not turning off my camera, so it's more easy for me to draw on this tablet. So before moving forward, just one or two clarifications or review what we did last time. We talked about still on the feedback topic. So we were on chapter 12 of fundamental of microelectronics, and we were doing the section 12.8 that was on feedback. And one clarification, in this course we are not covering section 12.7 that is talking about non-linearity of impedance. So section 12.7 is not included. Okay, so other than everything in chapter 12 we covered, but not section 12.7. Okay, so that we were not going to cover because that topic is not of, it's like more is related, but more towards a practical approach. So at this moment, unless we use those things, might not be that much beneficial. So that's why we're not doing that thing. But if you are interested, you can go through the topic and I will be able to answer any question related to that. But main thing what we did last time, we started the stability of feedback, which is section 12.8, stability of feedback system, rather stability of negative feedback system, because positive in our terminology is not going to be a stable system. So stability of a negative feedback system. And we said for any system which we have a drawing, we have A here, we have something output. If we are going a feedback of K going back here, and we have something plus here, a negative feedback system if we are having, and we said Y over X is a closed loop system, then the closed loop gain is equal to A divided by 1 plus KA. So let's make sure we all are comfortable with this thing where A is open loop gain. So we need some terminologies again and again. K is feedback gain. Just factor K, okay? And KA is a terminology which we call loop gain, okay? So let me point out all the things. This is A. So this one is A. This one is KA and this one is KA. And here this is the K. Just make sure these things are clarified. And the closed loop gain, yeah, that's the closed loop gain, because might be these things becomes confusing, which we just write here. A divided by 1 plus K. Okay? And we concluded previously something that I will just reiterate again about this thing. When KA is very much bigger than 1, then what happens, the closed loop gain A becomes equal to 1 over K for this condition. Okay? So these things which we have previously discussed. And regarding the stability of the, we defined two terminologies. One was gain crossover frequency, crossover frequency, and one was phase crossover frequency, WPX, phase crossover frequency. So what was gain crossover frequency? If we have any system and we have a magnitude, and if we have, let's say, we have a magnitude of loop gain. So here this is a loop gain Ka. I'm drawing the magnitude response using border plot of a Ka, and it is something like this one. The frequency at which this touches the 0 dB or the unity gain. ठीक है, नॉर्मल में यूनिटी गेन या 0 dB, दिस फ्रीक्वेंसी और ओमेगा इज नोन एज WGX, तो गेन क्रॉसओवर। जब मेरे पास जो लूप गेन है दैट इज इक्वल टू 1 या 0 dB, ठीक है। why is 0 dB? because 20 log of 1 is equal to 0 dB, ठीक है, ऐसे ही हो जाता है। so that's what we can write, and that point in the omega or radians per second is basically your gain crossover frequency. Similarly, we talk about phase crossover frequency. So let me just separate. So phase crossover frequency kya the? Omega px. Again, if we have something omega and we have some plot of the omega at which my phase becomes minus 180 degree, that point is known as phase crossover frequency. ठीक है, ये दो चीजें we concluded in the last time, and why they are very much important? Because let me just go to the next slide, because I want to reiterate again the same point that is very much important. We said okay, we have a closed loop gain y over x. It's a closed loop gain again, okay? Y over x is equal to a divided by 1 plus Ka. If we want to write in terms of omega or s, so that is something which we can write explicitly as a of s. It's depending upon frequency divided by 1 plus K times a of s. Okay, I can write this thing. So now we have this term which is K times a over s. So this system, which is my closed loop system, again, let me redraw the circuit. We have a here, we have output as y, we have a K, we have a plus, and we have a minus coming from here. In this system, if the product K times AFS becomes -1, what will happen? It will result into A over S divided by 1 minus 1, which will be equal to A over S by 0, meaning infinity. This means my system become unstable. And what does this mean? कि ये मेरा K times A over S -1 कब हो सकता है? When the magnitude is 1 and angle is plus or minus 180 degree. So that's something which we need to make sure. Okay, if my K of S is -1, this means mera magnitude is 1 and angle is 180 degree. So if these both conditions coexist at any point, this means my system is unstable. That's why we define these two terminologies of gain crossover frequency and phase crossover frequency. And what we do, we see the gain crossover frequency, meaning when my magnitude is 1. Okay? 1 meaning 0 dB. And my phase crossover when my angle is minus 180 degree. We see both these things. That's why we don't want these things to coexist, or we define for a system to be stable, my phase crossover frequency should be greater than gain crossover frequency. ये बड़ा होगा तो तभी I can ensure कि when this minus 180 degree comes, my magnitude is less than 1. if my magnitude is greater than equal to 1 at a phase of minus 180 degree, this means my system is unstable. So ये तो हम लोगों को condition you need to keep in your mind. This is must condition for system to be stable. अभी किस पे apply करना है? Should we apply on A? Should we apply on K? Should we apply on A times K? So we need to see. So definitely we are seeing this factor K times AS. That's why we need to apply A times KS. This condition we need to check on AS times K. So इस factor पे we need to apply this gain crossover frequency and we need to find phase crossover frequency. इसीलिए in order to check stability, in order, let me write because in order to check stability, we use loop gain. And what is loop gain? K times A. Product of open loop gain and feedback gain. ठीक है? Make sure your terminologies हैं, clarify them, which is just I mentioned also here explicitly. What is open loop gain? What is feedback gain? What is loop gain? And what is closed loop gain? ठीक है? So just reiterate these things, okay, why we are using and when we are using. So the whole point was that we want to again bring the stability condition. Okay, the phase crossover frequency should be greater than gain crossover frequency. We will do a couple of examples and then we will bring out some other notions that, like we are saying that, okay, phase crossover frequency is greater than gain crossover frequency by how much amount? So that we will define something in a phase margin too. But let me just move forward towards the example. I mentioned last time we'll do some couple of examples to clarify these things in real circuits. So 12.38 is one of the examples from your book, which is drawing some basic circuit cascade of 3 common source stages. So let me redraw the circuit and then we can analyze it. So we are giving this is, so it's basically 3 identical stages, meaning RD and value of the your MOSFETs and capacitance all are equal. So C1, these all are C1, and this M1, if I want to write M1, M2, and this M3, all of them are identical, meaning that GM1 is equal to GM2 is equal to GM3, and similarly RD all are same, and C all are capacitances, which is C1 are same, and this is point V out, and this one is V in. So we are given that M1 is equal to M2 is equal to M3, and another thing, RDs are already I mentioned they are same. So and so we want to do 2 things. First, A part, we want to plot the frequency response and condition for stability. For stability, when K, the feedback gain is equal to 1. So unity feedback. Okay. So we need to do the frequency response plot, meaning we need to have a frequency response using Bode plot, and we want to have a feedback loop which is K is equal to 1, meaning we have provided that this one something इसको इसमें कह देते हैं h j omega, the terminology your book is using. So we have V out, we have a feedback, which is unity feedback, and it's negative, and it is Vs. Let's not use the V in terminology. Okay, so Vs is at this moment the overall in a closed loop configuration, and h of j omega is basically the h of j omega hai, that is equal to V out over V in, which is open loop gain. Okay, though in this case open loop, okay, and the V out. So clarify these things. इसलिए I am writing is V out by Vs क्या है? That is h of j omega divided by 1 plus h of j omega. क्यों? K1. ठीक है? ये चीज make sure कर लें कि you are comfortable with these all things. Now सबसे पहली चीज क्या करनी है? We need to draw the frequency response. Frequency response में क्या करते हैं? A part में frequency response draw कर लेते हैं. I might need to redraw again in the next page because I need up and down, but it's okay. Let me draw these things. So we have omega here, which is in radians per second. And I have a magnitude first. So magnitude ke liye what I need to draw? Rather, let me just use the space above because I can draw the angle at the same point. And then let me just do this. I will squeeze the thing. And then I will redraw on the next page again. So that otherwise only plotting one will not help the cause. So at least we can do the A part here easily. Omega radians per second. So we have magnitude plot. So I am drawing again open loop. So I'm writing explicitly h of j omega magnitude. So we know that we have 3 poles here. Okay, we have 3 poles and we need to have some starting point, and then all of these 3 poles are lying at the same point. Since all of them, if we just see these node points, we have one node here. So omega p1 will be here, omega p2 will be here, and omega p3 will be here. And what are the values of all of these? So all values P1, P2, and P3 will be equal to what? Resistance time capacitance, 1 over RD C1. So now we know this thing. We have done this thing before in the frequency response. So ये तो हमें cutoff frequency पता चल गई. This means we are going to have something going like this. And this no point, which is here, ये point क्या होगा? 1 over RD C1. That's fine. All pole locations same. And what will be the slope here? Since all 3 poles are lying to the same point, Bode plot can help us that one pole do minus 20 dB per decade, 2 poles will do minus 40 dB per decade, and 3 poles will do minus 60 dB per decade. So we can have simply this thing. And another thing which we need, what will be the DC gain here at this point? So the DC gain, let me write with the blue. So the DC gain will be, what will be the DC gain? GMRDQ. So V out by V in, or h of j omega will be equal to, if I just want to write that omega is equal to 0, h j of omega, or it will be equal to GM RDQ. So this point, writing in the blue, DC gain will be GM RD whole cube mod. Okay, so 20 logs you can also mention. So this is going to be my, it's minus 60. This is going to be the magnitude response. And what will be the phase response? Phase response can be something like this. Again, we have omega radians per second. Currently, we don't know the value. So we can just do a plot something where these cutoff frequency we know and the DC gain we know. So we can just have, we know again, we have 3 poles. So the overall final angle where it will saturate will be minus 270 degrees. So I'm drawing a minus 90, minus 180, just for, and minus 270. This is not drawing down, but it will be something down here. So if we want to draw, so at 1 over RDC1 where the cutoff frequency is, this means at that point we have minus 45, minus 45, and minus 45. So overall minus 135 at this point. So it will start from some point, 10 times of this one, which is basically 1 over 10 omega p, which all are same. So it will reach to this one, and then it will go all the way to minus 270, and then it will stay here. So this is minus 270. So iski slope kya hogi? Minus 350 degree per decade, and the ending point will be minus 270 degree. So that is for the first part when we have to do the frequency response. I will again draw in the in the next page, and we need to find a condition for stability. So condition for stability will be what? In the form of the gain. What will, because हमारे पास variable क्या है? GMRD. कि GMRD को मैं कितना रखूं so that I can achieve stability. Stability की condition क्या थी? The same condition which you just said. Phase crossover frequency should be greater than gain crossover frequency. So let's go to the next page and redraw the circuit and then try to identify the part B. So I'm just redrawing again just so that we have a more better image. But the first again redrawing the frequency response. So we have this point, which is GM RD whole cube. Yes, we are taking 20 log here. Model. So we have starting from here, it will go to some point like this, will continue. This point where it will touch is going to be 1 over RD C1, and this is going to be minus 60 dB per decade. Okay. Then comes the second one. For magnitude and phase, we need to draw them like on the same scale sort of stuff, like up and down. So here I am drawing minus 270 degree, minus 180 degree, minus 90 degree. Okay, and here it will be somewhere minus 135 because that is important for us, and this is omega p 1 by 10, all are the same. So here it will start its ramp at this point, will reach to minus 135 here, and will go onwards minus 270, and then it will go straight. Okay, and iski jo slope hogi, that will be minus 135 degree per decade. So now we need to mention the phase crossover frequency, because phase crossover frequency we will find out, and we will find at the phase crossover frequency what is the magnitude. For a system to be stable at a phase crossover frequency, the magnitude, let me write this statement, at omega px, the magnitude should be, the magnitude from the gain, magnitude should be less than 1. Okay, less than 1, less than 1. This is a condition. Why is a condition? Because omega px should be greater than omega gx. And gx क्या है? Gain crossover frequency. यहाँ मैं 1 की बात कर रहा हूँ. I'm talking in terms of gain. So let's go back. So gain crossover frequency कौन सी होगी? Where the angle is minus 180 degree. So this point is omega px. First we'll do analytically, then we'll do quantitatively too. So this point is frequency is omega px is omega px पे if I go here and I determine इस point को omega px है ये मेरे पास, इस point पे the magnitude, if we say this point as a p, the magnitude at this point hp should be less than 1. मैं magnitude की बात कर रहा हूं, I'm removing the log at this moment just for simplification. The magnitude at this point should be less than 1, and that is the condition for stability. ठीक है? Just make sure this point is clear to you. Also go through the example 12.38 if not clear, but make sure this point is clear because that is very much important. So we know the qualitatively, if we set this condition, we can find out. So now let's put it and conclude the thing how it's going to be this way when we are going to figure it out. So we know our h of s or h of j omega is equal to dc gain gm rd whole cube divided by what is the thing? We have 1 plus s divided by omega p ऐसे ही है and the overall cube. So we have 3 poles. ठीक हो गया? Where one pole is at RDC1. And angle of this one, h of j omega, h of s, whatever we want to write, is equal to -3 tan inverse of omega by omega p. Clear है ये चीज? So at omega px, which is the phase crossover frequency, we know at omega px, what is this point? At omega px, my phase is -180 degree. जो हम लोगों ने यहाँ red में mention भी किया हुआ. This is -180 degree equal to -3 tan inverse have here omega की जगह omega px कर देते हैं, and this is at omega t, right? So this will be cancelled out, so it will be tan inverse omega px by omega p equal to 60 degree, which will mean that omega px, the phase crossover frequency, is equal to √3 omega p. tan 60 is √3. So ये हमारे पास एक condition आ जाएगी, ठीक है? Now we need to put this condition in the magnitude one. Magnitude हम लोगों ने क्या कहा था? At omega px, magnitude was h of p, जिसका हम नाम दे रहे थे h of p, जिसको हम लोगों ने कहा था it should be less than 1. Magnitude क्या होगा? gmrd will remain as gmrd. वन प्लस j ओमेगा की जगह क्या आ जाएगा? s की जगह j ओमेगा आ जाएगा, तो इसकी जगह ओमेगा की जगह क्या आ जाएगा? At what frequency we are seeing? Basically we are seeing at phase crossover frequency, which is omega px for us. So we need to bring out omega px here, ठीक है? तो मैं इसकी जगह लिख दूंगा 1 plus omega px divided by omega p. Okay, now you might be seeing something, and what I need to write the magnitude, so scale 4, and then we have to have a cube. So make sure this thing is clear again. Yeah. Okay, so I will draw, right, let me do this thing. I will go on the next page and write both of these to 1, 2 again, and then start from the same point. So we concluded that one expression was the omega px phase frequency was equal to √3 omega p. That's first thing. And the second thing which we just reached, that gm rd whole cube divided by 1 plus omega px divided by omega p whole square √whole cube, which was now hp, ठीक है? hp What should be? It should be less than 1. Clear it? Less than 1 kyun hoga? So that we can have our system stable. What we mean, we can put 1 in the 2. So it will be GMRD whole cube divided by 1 plus under root 3 omega p by omega p square q less than 1, which means GMRD whole cube omega p will be cancel out 3 square 3 and then under root, so it will be something 4 cube should be less than 1, meaning GMRD whole cube should be less than 2. 4 under root 2 and cube, so it will be like this, and GMRD should be less than 2. So this is a condition. So in order for the system to be stable, my open loop gain of individual states should be less than 2, or the net open loop gain should be, GMRD should be less than 8. So that's the condition for stability. Condition for stability. There is a follow-up example, I guess all of you should do. That's also very much interesting. Is 12.40 example. So in 12.40, they are changing the K to, at this moment they put K is equal to 1. So they're saying if we do the K is equal to half, what will happen to the system? So I would highly recommend all of you to see this thing on K is equal to half, how the response changes, because that how the stability changes is the open loop gain relaxes or becomes more complex. Make sure to do this thing. And if there is some confusion, just you can discuss in the office hours. So now this brings us to another topic, which is also from stability, is a phase margin. Currently, what we talked about, we mentioned that just phase crossover frequency should be greater than gain crossover frequency. We didn't mention that, okay, how much, because that's very much important. If I draw pictorially, if we have some plot like this of omega magnitude हो गया, ये मेरे पास phase हो गया omega. So my gain crossover field, this is 0 dB है, ये मेरे पास I guess I need to go opposite way. So यहाँ मेरे पास -180 degree है. So if I have something like this one, तो मैं कहता था कि this frequency is my omega gx. ठीक है, ये हो गया था. और फेस क्रॉसओवर क्या कहते थे, अगर मेरे पास किस पॉइंट पे ऐसा पॉइंट है इस पे मेरी फ्रीक्वेंसी मीट कर रही है, ठीक है, तो दिस वाज ओमेगा px. अगर मेरे पास ओमेगा px इज इक्वल टू ओमेगा gx हो जाए तो क्या होगा इन योर ओपिनियन? So what I am saying, if omega px is equal to omega gx, if I have a system which is h of s and the response is y, I have a feedback k going here -1, and this is x. So what I am saying here, that if I have this sort of system and I have y over x is equal to h of s divided by 1 plus k h of s. If this condition happens, gain crossover frequency is equal to phase crossover frequency, meaning this is equal to -1, then my system is unstable. But how it will look like? It will oscillate. How it will oscillate? It will be like this, consistent oscillation. This system have an oscillatory behavior. Omega gx is equal to omega px. If they both are all the time equal to each other, my behavior will be oscillatory. Okay, it will oscillate like clock. साइनोसाइड जनरेट करते हैं. So it will be something similar. That's why it's an oscillator. ठीक है. Whenever this condition is going to be, this is for stability condition. But यहाँ अगर ये condition हो तो this is an oscillatory condition. ठीक है. My system will oscillate. So this means यहाँ तो मुझे ये मेरा system stable नहीं है. ठीक है. Let me rub this thing to clarify. यहाँ तो अभी system मेरा unstable है. So this system is unstable. What about other condition? Let me just bring a little bit near to each other. If we do this thing, कि मेरे पास ये आपके पास था, and this is your magnitude. So we just draw कि ये मेरे पास gain crossover था, and ये मेरे पास somehow phase crossover था. Gain तो ये आ गया. अगर phase is greater than gain, meaning यहाँ इसको -180 मिल रहा है, but though the omega px ये 0 है, this is omega gx, though omega px is greater than omega gx, but the margin is less. If my system is something like this, कि omega px ज़्यादा तो है omega gx से, but इतना ज़्यादा नहीं है, this means my phase margin is less. So system response will be like this. वो जाएगा, but there will be ripples, or it will take some time before it gets stabilized. ठीक है, in this condition. But अगर मेरे पास system ऐसा हो, shown here, if this is my gain crossover frequency and this is my phase crossover frequency, which is far, good amount far. This is omega gx. This is omega px 0. If they are far and omega px is greater than omega gx by good amount, अब क्या होगा? My system response will be like this, stable. This is stable. This is also stable, but ripply. They are ripples. I don't like this system response because they are ripples. It will take some time before it settles down. That's why we define a terminology which is known as phase margin, that we need to give some margin between these two quantities. And what is that? The way how we decide this thing? Based on, again, the loop gain. So we use the loop gain and we put some margin in the loop gain. So if I want to decide what is my phase margin, PM, phase margin is defined as, it can be anything, but I will just tell you what is a reasonable value. But let me just define it. Phase margin is equal to gain crossover frequency of a system, h of gain crossover frequency, plus 180 degree. Okay. So this is the definition of a phase margin. Now, how much is a good phase margin? Normally, when we write omega gx is equal to omega px, somebody says, what is your phase margin? This means 0 degree. There is no phase margin you have. So for a good system, the phase margin should be between 45 degree to 60 degree. 60 से ज़्यादा हो तो और भी अच्छा, लेकिन 45 should be a good number. Less than 45, the systems are not stable. In amplifier, we at least make sure our phase margin is 45 to 60 degree. Now you can say, okay, why 45 degree? Why not 30 degree? Might also be system stable. We have to keep margin for the variations, for the PVT variations too. So that's why for us, the phase margin should be 45 to 60 degree. And we defined using this formula. And sorry, यहाँ एक mistake मैंने की है. It's not h of g. It's going to be loop gain, meaning a times h of w gx. Gain crossover frequency of a loop gain plus 180 degree. And that's what we are going to use all the time. Okay. So we will use this one to check the stability of a system. Stability of a system. Right. Now this brings us to another point, I guess, which is related to some examples, I guess. So we can do a couple of examples, and that is somehow related to the frequency compensation. So frequency compensation. So we come to another topic, which is a frequency compensation. So what I will do, I will just describe the frequency compensation now, and we can do some couple of examples in the next lecture, because I guess so you can adjust all the things which we have discussed in today's lecture. And I also want to give an overview about feedback, closed and open loop in the next lecture again, just to summarize everything. So coming back to the frequency compensation, we have seen basically that if we have a system which is somehow like this one, we have a system like this, where the gain crossover frequency is here and the phase crossover frequency was somehow like this. Okay. So this is the omega px and this is omega gx. So our point was that at this moment, if we are given a task, okay, your phase crossover frequency is here, gain crossover frequency is here, and your phase margin is 30 degrees. I'm just putting some numbers. And somebody tells you need to improve your phase margin because it's less. This means ultimately what we need to do, we need to take the gain crossover frequency this side, or we need to shift our dominant pole towards the left. If I'm making my dominant pole on the left hand side, this means I'm bringing the pole earlier, and the gain crossover frequency will go on the left hand side, or ultimately meaning I'm reducing my bandwidth. जिस तरह हमने पहले बात की थी, gain bandwidth product is constant. So if I have my system unstable and somebody says you need to make your system stable, this means you have to compromise your bandwidth somehow. ठीक है, आपको कोई ना कोई चीज compromise करनी पड़ेगी to make your system stable. So we will compromise the bandwidth and shift our dominant pole on the left hand side earlier, so that my system can become stable. So that technique is known as frequency compensation. We need to compensate something based on some stuff. And what is that? Stability. अगर हमने achieve करनी है, we have to reduce bandwidth, or we have to reduce the speed of the system. अगर हम layman terminology में कहें, आपका system stable नहीं हो रहा, you need to slow down. Slow करेंगे तो system stable हो जाएगा. Something similar. You accelerate the car, you are driving at 120 kilometer. Okay, you are in well control. You drive on 140, 150, you start losing your control. Now, if somebody says make your slow down so that you get a control on your system, this means you have to make your system stable. The same concept. अब bandwidth ज़्यादा है, bandwidth का मतलब क्या है? Your frequency ज़्यादा है, frequency का मतलब क्या है? Your speed is more, so you need to reduce your speed. So we will talk about this thing in the form of examples, in the form of circuits in next lecture. And we will do examples to close the overall feedback concept. But till now, if you have any query, concern, make sure to come in the office hours or send an email. We can have a separate session. Or also normally what I do, I do the lecture during office or during the normal class time most of the time. So you are more than welcome to join in that window too. So let me try to save, if I can save this. Thank you for your attention.